Hi everyone, it's B again. This lesson is all about logarithms. Now that we've used logs for 5 lessons in a row, it's time to learn how to evaluate logarithms without a calculator and how to solve logarithmic equations. Let's get started. At the start of your lesson, you had the pre-video activity, Matching Powers. If you haven't had a chance to work on it yet, pause the video to do that now. Throughout this lesson, we'll be using the properties of exponents, which you have at the bottom of this page. Feel free to refer back to them whenever you need a refresher. Let's dive right into some log problems. We'll start off with example 1, which you have in your guided notes section. Let's figure out how to evaluate these logarithms without using a calculator. First, we have log base 3 of 9. Remember that a logarithm is asking for the exponent to which we raise the base to get the argument. So in this case, we're looking for the exponent that turns 3 into 9. What would that exponent be? That would be 2. Therefore, log base 3 of 9 equals 2 because 3 squared equals 9. Now let's do log base 2 of 1 over 8. What is this logarithm asking for? It's asking us what exponent turns 2 into 1/8. Well, I know 2 cubed is 8, but what exponent would give us 1 over 2 cubed? There is a property of exponents that tells us a negative exponent turns a number into its reciprocal. So the exponent that turns 2 into 1 over 2 cubed should be negative 3. Therefore, log base 2 of 1/8 equals negative 3 because 2 to the negative 3 equals 1/8. Let's move on to the next one, ln1. Pause the video and try it yourself. We recently learned that ln means log base e, so we need to find the exponent that turns e into 1. Another property of exponents to the rescue. We know that, in general, a number raised to the power of 0 is 1. So ln1 equals 0 because e to the 0 is 1. Now let's evaluate log of 0.01. Wait, log base what? This logarithm apparently has no base. Just like ln is shorthand for log base e because we use it so often, there's another logarithm that is so common that it has its own special notation. This is the logarithm base 10, which is called the common logarithm and written as just log of x without a base subscript. Therefore, we know that log of 0.01 is actually saying log base 10 of 0.01. So we must find the exponent that turns 10 into 0.01. How can we express 0.01 as a power of 10? Well, it'd be helpful to first rewrite this decimal as a fraction. 0.01 is the same as saying 1/100th. And 100 is a power of 10. It's 10 squared. Now we can use the negative exponent property once again and express 1 over 10 squared as 10 to the negative 2. Therefore, log of 0.01 is negative 2 because 10 to the negative 2 is 0.01. Let's look at 3 more logs. Log base pi of pi, log base 16 of 2, and log base 5 of 5 squared. Pause the video and try to work them out yourself. Remember, the properties of exponents might be helpful. Log base pi of pi is the exponent that turns pi into pi. we know that any number to the power of 1 gives us back the same number. Therefore, log base pi of pi equals 1, because pi to the 1 equals pi. Now part F, log base 16 of 2. We need the exponent that turns 16 into 2. This one's tricky. I know 16 is a power of 2 because 2 to the 4th power is 16, but we need 2 as a power of 16. Well, if 2 to the 4th power is 16, that means the 4th root of 16 is 2. That's helpful because we have a property that allows us to translate between radicals and exponents. We can write the 4th root of 16 as 16 to the 1/4. Therefore, log base 16 of 2 is 1/4 because 16 to the 1/4 is 2. Lastly, let's evaluate log base 5 of 5 squared. What exponent turns 5 into 5 squared? Well, that's just 2. So log base 5 of 5 squared equals 2 because 5 squared is, well, 5 squared. The last logarithm seemed kind of redundant, but it actually reveals an important property. Since there was a power of 5 inside a log base 5, the result was simply the exponent of the power. In general, we say that log base b of b to the x is equal to x. Earlier in this unit, we also saw how any base raised to a logarithm of that same base gives or releases the argument inside. The action of turning a number into the exponent of some base is often called exponentiation. So in this case, we can say log base b of x is being exponentiated with base b. Do you see any relationship between these two properties? As long as the bases match, a logarithm releases the exponent of the power inside. And raising to the power of a logarithm releases the argument inside. It seems like taking a logarithm undoes exponentiation. And exponentiation undoes a logarithm. Therefore, given that the bases match, taking a logarithm and exponentiation are inverse operations. Let's try to apply these two properties to find the value of ln of e to the 6 and 10 to the log of 3. Pause the video now and try to evaluate these expressions yourself. Since we are taking the natural logarithm of a power of e and the base of ln is e, the answer is simply 6. In the second one, since log 3 has a base 10 and it's being raised as a power of 10, the answer is just 3. These relationships also give us very useful strategies to solve equations where it's necessary to undo a log or undo exponentiation. Let's see how that works out in example 2. We will solve an exponential equation, which is simply an equation where the variable is an exponent, and a logarithmic equation, which is an equation where the variable is in the argument of a logarithm. Let's first consider the equation 5 to the x equals 3. Since we're looking for the exponent that turns 5 into 3, we already know the solution is log base 5 of 3. However, let's try a different way of approaching this equation. Remember that when solving equations, we make use of inverse operations to isolate the variable. For example, to undo subtraction, we perform addition on both sides, and to undo multiplication, we use division. Could we use this same concept here to release the x from being trapped as an exponent? We can use the property that shows us how to undo exponentiation with a logarithm. Here, the x is acting as an exponent for the base 5. If we want to undo this exponentiation, we can take the logarithm base 5 of both sides. On the left side, the log undoes the exponentiation and gives us that x equals log base 5 of 3, which is the exact same answer we got with our previous strategy. Later on in this unit, you'll see that this strategy of taking the logarithm of both sides is often more efficient when solving more complex exponential equations. Now, what about undoing a log with exponentiation? Let's try it out with the equation log base 5 of x equals 2. Remember that the second property showed us how to undo a logarithm with exponentiation. Pause the video and try to apply this property to solve this equation. If we want to release the x from the logarithm on the left, we can undo the logarithm by exponentiating both sides with base 5. On the left side, the x is released from the log, and we get x equals 25. Now let's look at another strategy to solve exponential and logarithmic equations. To understand this strategy, let's formalize the relationship between exponential and logarithmic equations that we've actually already been using without realizing it. Let's rewind to the first logarithm we evaluated in this lesson, log base 3 of 9. We said that log base 3 of 9 was equal to 2 because 3 to the power of 2 is 9. These two equations are in fact equivalent. That is, they represent the exact same relationship. This double-headed arrow is read as if and only if, and it means that if either one of the statements is true, the other one has to be true as well. And if either one is false, both are automatically false. In general, we say that log base b of x equals y if and only if b to the y equals x. In other words, if and only if the base of the logarithm to the power of the result equals the argument. This concise statement gives us a very straightforward approach for converting between an equation in logarithmic form and an equation in exponential form, which is a great strategy to solve equations. Throughout this whole unit, we have been using this relationship to solve exponential equations. For example, when we solved 5 to the x equals 3 and got x equals log base 5 of 3, we basically just converted from exponential form to logarithmic form. Now let's use it to solve logarithmic equations in our next example. Example 3 says, solve the logarithmic equation by rewriting it in exponential form. Our equation is log base 2 of x minus 5 equals 3. Before we work it out together, try it out yourself. Here's the relationship to help you convert. Pause the video now and give it a shot. The exponential form of this equation would be 2 to the power of 3 equals x minus 5. We can write 2 cubed as 8 and then add 5 on both sides. Therefore, x equals 13. What's another way we could have solved this equation? Now that we solved it by rewriting it in exponential form, let's see how it would have played out if we had solved it using only inverse operations. We'd exponentiate each side with base 2, and once again we'd get x minus 5 equals 8, which of course leads us to x equals 13. Let's wrap up this lesson with one final example. Solve the logarithmic equation, -1 equals 5 minus 3 log base 7 of x squared plus 13. It looks like this equation requires some cleaning up before applying one of our strategies. To make it look like the log equations we've been solving, let's isolate the logarithm. We might be tempted to first subtract the 5 with the 3, But since the 3 here is multiplying with the logarithm, that would go against the order of operations, which says multiplication must be done before subtraction. Let's instead get rid of the 5 by subtracting 5 on both sides. Then we can divide both sides by -3, and we get 2 equals log base 7 of x squared plus 13. Pause the video and finish solving this equation with whatever strategy you prefer. I'll choose to solve it by rewriting it in exponential form. We get that 7 to the power of 2 equals x squared plus 13, and 7 squared is 49. Seems like we ended up with a quadratic equation. I always like to try to solve these by factoring first, and if that doesn't work, then I complete the square or use the quadratic formula. To solve by factoring, we need one side to be 0, so let's subtract 49 on both sides. We get 0 equals x squared minus 36. This quadratic expression looks like a difference of squares, so we can factor it as x plus 6 times x minus 6, which makes the solutions x equals -6 and x equals 6. In this lesson, we learned about how, given same bases, taking a logarithm and exponentiation are inverse operations, and we applied these properties to solve both exponential and logarithmic equations. We also learned how to convert between logarithmic and exponential forms of equations by using this relationship, which neatly summarizes the connection between logarithms and exponents. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time!